All right. We will just quickly go back to our exercise from last Wednesday. So last Wednesday, I solved the bisection method for parachutists in the class and posted it for you. And then I asked you to actually apply this bisection method and solve it for this polynomial right here. F of x is x cubed minus 5x squared plus x plus 2.5. Now, one thing, so the way bisection method works is that you have to find an interval. A good bisection interval has, when I take a value of the function on one end of that interval and value of the function on the other end, they have opposite signs. So mathematically, f of xl times f of xu, we call this xl and xu, is less than 0. Okay, so I need to test that. And then I actually keep halving this interval and finding which of the halves is still preserving that property. That my function on one end, f of xl times f of xu, is less than 0. And I keep going until I get close enough. Okay? Now this close enough is somewhat up to me. Okay? I can check that my interval is small enough, so I'm close enough to the root itself. I could possibly check that value f is close enough to 0. So I can say, okay, in value, you're 10 to the minus 16 or something like that, that's close enough. So it's close enough, what's close enough to you. So in some sense, you decide when to stop, and that's basically how accurate your method is. Now, one of the key things, so basically if I wanted to just change that parachutist problem to this, what I call this now, roots of polynomial, the way I wrote the function last time, I actually have this function fx, which computed there was that complex function for parachutist, and all I really need to do to solve any other problem is to change that function, which is why it's good to have a separate function computing whatever function you have, f of x is equal to 0, because I went in there, I changed it, and the rest of the code remains the same. So I have here compute f, it's now a different f. Only this function sees compute f because it's the second function in my file, so it's sort of a secondary function, so only this file sees it, so it's not going to mix it up with the other compute f. And second comment I want to do here is first we plotted the function because you do have to find the interval. So one thing that technically this bisection method depends on is that you have to have a starting interval. Now if I use the starting interval that I had before in that parachutist problem, it's not necessarily going to work. If I run this, it's going to tell me something's fishy. And that's why it was good to have that display here. So I kind of never figured this out. And the main problem was that my starting point are 12. Oh, for once, I actually plotted only till 10. So if I plot this, I can actually see that my function values are all positive in 12 to 16. So therefore, it's not a good starting point. If I don't have a good starting point, my bisection method will do nothing. So take home is that I always have to actually pick the values correctly. So you will have to plot the function and take a look. So if I actually zoom in here, I see that I have a 0, however, slight 0, but I am intersecting 0 here, between 4 and 5. So 4 and 5 is a good interval. I will go back to then plotting up to 6. Okay. It's a good interval, and let's actually now do it. Nothing's fishy now. Okay. So this is why it's good to have those warnings, go back and check what's going on. Or just go fishing. So basically, I zoomed into this on this root 4.67 in 14 iterations. Now, is that all of the roots that I have in this function? Okay. Seems that I have some roots over here, and I actually didn't plot anything up until 0. So actually, I don't know. Okay. I'm going to, with bisection method, find only the root, one of the roots that is within that interval. Okay. And I don't even know which one. So it kind of depends. Let's actually try to explore this function a little more. Technically, it's a polynomial. It's cubic polynomial. It has up to 3 real roots. And I actually do seem to see 2 here at least. Let's see, actually, let's zoom in a little. So I'm actually going to now plot this function from -10. Okay. So -10, I have a crossing rest, maybe -4 is enough. Let's just zoom in a little more. So I have one crossing here, 1, 2, 3. Okay. So initially I found this one 4 to 5, but there is actually one here and one here. This one is between -1 and 0. Let's try to find that one. But for that, I have to have this XL and changed. I'll call this. So now I found this one, which is about -0.6. Okay. And now obviously I'm changing the start XL and XU of my bisection. So in this, my playing with it, it became obvious that actually those would be very good inputs to the function. Okay. So I'm actually going to put them as input to this function and change it. XL, XU, okay, and this is, okay. And now I'm going to remove this interval, okay, because if I leave it there, I'm going to overwrite it, okay. So be careful when you have a function and it has input variables. If you overwrite those variables within the function, then whatever you gave the function as an input will be of no importance. Okay? So I don't want to overwrite it. Okay? And I'm going to put comments here that input variables are XL, XU, okay, left and right and, or lower and upper, well, points. And since I'm doing it that way, then I'm also going to plot the function from XL to XU. Okay, let's execute now. So now if I run it from here, I'm going to have trouble because the way I compose the function now, it actually has inputs. So I'm going to give it -1 and 0 and find this root, okay, which is around -0.6. And then there was another one between 0 and 2, correct? Let's try. That one is 9.91. Oh, it just added to it. Okay. I guess I'm having hold on active without noticing. Let's actually now do 2 to 6. Yeah, hold on is active in my... I didn't turn off MATLAB since last class. Okay. So basically now I just kept adding to it. Questions? Okay. So I need to have a starting interval. I need to find it, and for that I often need to just plot the function to find out what the good option would be. All right. You have one method. This one, if you actually have that interval, this one is good. It's going to find a result. Okay? It's going to find you error. Now, one more thing that I would like to ask you now. So here I went with this absolute XU minus XL larger than tolerance, which is essentially my absolute error. How would I change this if I actually wanted to do relative error to be less than some tolerance? It's up to me which of the errors I use, right? What is relative error here? I could divide it by XU, so this is approximation. I don't know the result, so I don't have true value. Okay, so just take my last two estimates and figure it out. Now, this is now almost a philosophical question: do I use XU, XL, and XU, or do I use XR? Right? Well, XR is your new value of XU, so you're maybe off by one iteration in that case. It's not a big deal in numerical. Being off by one iteration in a numerical method is not a big deal. Okay? You are just getting closer. So as long as you use one of them. So technically, I could have actually computed error. So I'm going to say error. Something like this. I would have to be a little more careful if XU, and I should actually have a check. If this is a 0, then it can cause a problem. So it's initially infinity. But that should change closer. And then if error is larger than tolerance, and then I can actually recompute that error. Okay, so this is one option of changing things. And I could actually have XR and error as an output. This is now options on modifying and computing error. Okay? One more quiz question. Let's say that I wanted to see how does this error change iteration by iteration, and I want to plot that. So this interval is getting smaller, 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 and smaller. Okay? How would I do that? How would I modify my code?
I was going to answer you how you could plot it with iteration and
So I could actually record this error for every iteration. Right? So I can actually record an array and then plot it at the end. Let's do that. So I'm going to say error of, I'm going to actually say error is 1. So error of iteration okay? And then now I'm recording all of them. Okay? So let's actually execute that. So I'm going to record, and to get that second output out, I actually need to now write this way. So now I can actually see, I'm just going to plot error. If I just plot error, it's going to plot it against the number of values, right? Okay. So I can actually see my error going down, okay? In absolute sense. It's actually also very common to see, in order to see how small does it really get when it's small, you need a logarithm. Because the error will start being in the order of 10 to the minus 5 and 10 to the minus 6 and so forth. In order to see actual what's happening in that lower end of the graph, it is very common to put error in logarithm. Okay? So basically, I'm going down to 10 to the minus 4, And I think the tolerance I asked for was 10 to the minus 4, so I'm not going to go below that. Okay. Questions? Well, the reason why I actually want to plot error and how well it does, because we have to have a way to evaluate how good is my method. I'm about to introduce 4 more methods for finding roots. And we ultimately want to be able to compare which one is the fastest one, which means how fast do you get to very small numbers of errors, okay? So in order to be able to compare, we actually have to compare the performance of these methods by looking at how fast does this error drop down. All right, let's get to it. So this was the bisection method. One of the errors, one of the ways to, and I'm going to be careful in using improve for some reason. I'm going to be careful in using improve performance because there's no method that works really well for all of the possible problems because we never know what is the function that is coming up our way. And I cannot find a method that works great for all the possible functions there. Okay? So that's why I will give you a range of possibilities. And I said 5 total, so you will have to often compare how well they do. So normally in practice, let's say that your manager down the line tells you, okay, solve the problem, and you actually figure out that solution to this problem is finding a root of some sort of function. Sometimes you need to optimize some performance, and that's going to be root of a function. So you will go, and you will actually explore, I would say, at least 2 to 3 methods that you will pull out some of these, dust them off, and put together, change your function to be the one you want. And then you will go and solve it, and I say compare the errors or how fast does it work in some common types of situations that you will actually be solving, and you will see that one of those methods works the best. And then you kind of hard code that method and use it for that entire project. And presumably you're going to execute it 5,000 times. So of course, if you're executing something 5,000 times, you do care that it's faster than some other option. Especially if it might take, here, this is 14 iterations, everything works. You have that much time to wait, okay? But if you have a problem that you're constantly solving and you're actually going through a log, and that log has 5, 6, 7, 8, 10,000 entries that you have to go through, things are not going to work in 1 second. They might take an hour, okay? So in that case, you actually care about performance and being faster, so you'll go and evaluate which one is the best, and that's what you're going to use. That's sort of like a common sense approach, is valid for any numerical method, whether you're finding roots or anything else. You're going to test a couple of them, see which one behaves the best in the situation that you think you want to apply it in, and then you're just going to go with that, okay? So this is second option. It says, all right, well, this is my function. Let's say that I'm looking for the root of this function, okay? So instead of just halving this interval, which is what bisection method does, can I actually see to speed that up and get kind of closer and zoom in on my root faster? And one option is, which sometimes works rather well, is okay, well, if instead of looking for I'm looking for this root, and normally my bisection would give me this as my next interval, right? This. Well, if I actually just do a straight line, which I always can between these two ends, I can maybe go faster or go there faster if I'm just looking at the intersection of this line. And this line is really just the first order approximation of my actual function. Okay. So this is just an approximation of this function in terms of a straight line if I had 2 points. If you do that and you're now wondering, so maybe this is my next XR. Okay, what is that next XR? I'm going to find it geometrically if I look at this length over here, f of xl, compared to this length, xr minus xl. That has to be that ratio, since this corner is equal to this corner, that ratio has to be the same as f of xu divided by xr minus xu. That's it. So that's how I'm actually going to find when this is my equation, and I was actually careful here with the signs. So my f of xl here is negative. So this value here is negative. This value here I took as positive, xr minus xl. And this f of xu is positive, but I took this one as a negative, xr minus xu. So this is a negative number, this is a negative number. I should work things out well, otherwise I have a mistake. So I can actually just compute what xr is over here, and that's my next value of xr instead of taking one that I had in bisection method. Okay. So this is just replacing how do I find that instead of a midpoint, this is the point that I'm taking. And I will still check which of the intervals is good interval. Remember that the good interval actually takes, you have to have a negative times a positive value for interval to work. Okay. So that is one method, and this is where I say, okay, this is, now that I have two methods that I could possibly use, we would actually go and check which one is faster, and I would plot those error values. Most often, now the example that I showed, my errors kind of went straight down when I plot them on log plot. Okay. That's actually a very good convergence. Most often, bisection is not going to perform very well. And the reason why it performed really well on that problem is that I had a polynomial. Polynomials are nice, okay? They're not too complex. But if I had a more complex function, or if my function near that root was not very well behaved, then I might actually have a zigzag in errors. Okay? Whereas Paul's position, if it actually, when it finds the root, it often finds it fast. Will it actually perform this particular way in the problem you're looking at? You never know until you see the function. Okay, so be aware of that. So essentially, if I actually rearrange that other formula, my xr will be xu minus f of xu times xl minus xu divided by f of xl minus f of xu. So let's briefly go to either that polynomial or parachutist, whichever problem you prefer, and basically replace that bisection method, save it as a new file, and do your false position. And I also want you to modify script to compute relative error. Now we have only 3 minutes left, so but let's nevertheless work on it. Do you want me to post this one so you can, because there's errors already in there. All right, I'm gonna post that. Canvas. This is how many emails I get by being offline for 30 minutes. All right, Canvas. So if you ever wonder why I didn't respond to your email, because I get them at the rate of 20 per half an hour sometimes.
So what method you use, is it just dependent on which one gives you the answer faster, or accuracy as well?
Accuracy as well. We're going to get to that when we actually get to more accurate method. But that's something that, I mean, in terms of accuracy, if you're just saying how close do I get to my root, that's the tolerance that I typically prescribe. So all of them can get within 10 to the minus 5 relative error within my root. Okay. But some of them will get them very fast, and those I regard more accurate. Okay. But they're really, the term would be converge. They converge faster. So how fast I get there is convergence, and whether I actually get to a root or close to it. And accuracy is how close to the root did I get. So those are two important aspects of every numerical method. Okay. So let me just, I'm going to upload roots polynomial to MATLAB. Okay, so you can now download it. I called it roots polynomial So I'm gonna call my false position. And my MATLAB wants me to reflect correctly. So I'm not gonna ask you to upload this one because it's spring break, but do work on it if you'd like. So basically just modify this bisection method to work as false position method, and we're gonna comment on it on Monday.